So hello everyone and welcome to part 1. My name is Aaron Danner and I'll be teaching you about the use of various materials in electronics. I've got some interesting demonstrations to show you throughout the class, and I hope that you'll enjoy the lectures. The properties of materials often depend on things that can't be seen, like electron configurations, and for this reason electricity has always been a bit mysterious given that it's invisible. So we're going to start with some larger concrete objects to review a few important physical concepts like energy and power before we start talking about more abstract concepts. This outline will give you some idea of where we're headed. The first thing I want to show you is the great Laxey wheel, also known as Lady Isabella. This is a giant water wheel, the likes of which were commonly used in the Middle Ages to provide a source of power before the invention of coal-fired steam engines. Water mills were the way that most of the world was able to harness power in the past. This is one of the largest ones ever constructed, and it's still in existence on the Isle of Man in the UK. In fact, this is the largest operable water wheel in the world, and it was built in the 1800s. Although they had steam engines at the time, the Isle of Man didn't have a good source of coal, so the water wheel was still a solution. So at the height of the water wheel building era in Europe, there were probably thousands of such wheels. In other words, not very many. Each village might hope to have 1 or 2 water mills that could be used either for agricultural reasons, or in the case of the great Laxey wheel, to pump water up out of a mine. And what I'd like you to notice about the video is how incredibly large this is and how difficult it must have been to construct. Look at all the stonework. To be able to build all of that without the aid of modern technology is really a marvel. So that's the situation before electricity. I think what's also really interesting about this wheel is the amount of power it can harness. Let's now calculate the output power of this water wheel. So it was built in 1854, and I actually chose this particular water wheel because it happens to be really large. It's said that this water wheel can pump 1,100 liters per minute from a mine 460 meters underground. From the potential energy difference of the water that it lifts and how often it lifts that amount of water, it's possible to calculate the power output of the wheel. Let's go ahead and do that. So we have water that's at a lower point in the gravitational well, and the job of the Laxey wheel is to pump the water to a higher level. And this requires energy, and we can calculate how much energy is necessary to move that water because we know that the water gains potential energy when it's pumped up. The height difference in this situation was 460 meters. And we can calculate the potential energy that the water gains when it moves up that height by using the equation for potential energy, which is mgh, where m is the mass, g is the gravitational acceleration of the Earth, and h is the height. So we can start inserting the numbers we know into this equation. We were told that the Laxey wheel can pump 1,100 liters per minute. 1,100 liters of water weighs 1,100 kilograms, so the mass here should be 1,100 kilograms. And gravitational acceleration of the Earth is 9.8 meters per second squared. And the height difference is 460 meters. So if we multiply these 3 numbers together, we get 4.96 megajoules. And I conclude that every minute, the great Laxey wheel supplies 4.96 megajoules to the water in the form of the added potential energy. Let's calculate the power. So the power supplied by the Laxey wheel, or energy per unit time, is 4.96 megajoules every minute, which is 60 seconds. And I've put it in seconds so that the units come out to something we're familiar with. So 4.96 divided by 60 in the correct units is 82.6 kilowatt. So the Laxey wheel supplies 82.6 kilowatts in order to pump the water. I think it's very interesting that a wheel that took such a large amount of effort to construct, in terms of all that beautiful stone masonry, can only give you a similar output power as a small car engine. And if you think about the amount of power that each individual in human society today can harness, it's really amazing. The engine of a Ford Pinto and any modern car really delivers roughly the same output power and would be able to pump the same amount of water as that of the wheel. And there's a lot more cars around than there are water mills. The Ford Pinto, in my opinion, was one of the worst cars ever made. I don't know if you've ever heard of the Ford Pinto before, but it had kind of an unusual design here at the back. Unfortunately, the petrol tank was placed, some might say, a little bit too close to the rear bumper, so the car had an increased likelihood to catch on fire in rear-end collisions. It's kind of an interesting case in engineering ethics, because some employees at Ford Motor Company at the time had calculated how many people were expected to die due to burn injuries from rear-end collisions due to the design flaw and the cost to society of losing those human lives. And then they compared that cost to how much it would cost to do a product recall and improve the situation with the tank. So those issues were captured in a very famous memo called the Pinto Memo. And as you can imagine, once the memo was made public, it was a public relations disaster for Ford, as a number of people had died in rear-end collisions at that point. The final result was the largest recall in automotive history. What we've learned in this video is that it takes energy to lift something out of a gravity well. What we can say equivalently is that non-moving objects that are higher in a gravity well have more energy than objects which are further down. The concept of energy and gravity wells, which we just reviewed, will be useful later on when we start talking about potential wells and electron orbits, because the same concept applies. You can think of an atomic nucleus as an electric well, and it takes more energy to pull an electron out of an atom if it's orbiting close to the nucleus compared to an electron that's orbiting at a greater distance. In the next video, I'll describe the origins of electricity, and we'll start to talk about static electricity in particular. We'll start to think about some of the origins of electrical conductivity and what makes some objects more conductive than others.